Hey everybody, we're going to dig into chapter 4, which is on models of the atom. In this one, we're not going to do as many sample problems because they're more conceptual. We're going to save those for the session on Monday, Tuesday, whichever section you're in. And then it may make sense to go back and watch the video and then do some practice. So it's a little bit different. It's not as math intensive. It's much more concept based. So you'll need to be able to read through the questions and, reason out your answers. So again, chapter 4, a little bit different. We're talking about models of the atom. We're going to go through a little bit of a history lesson first before we start talking about more concepts. Here we go. So the idea of atomic theory goes back pretty far. There's a Greek philosopher named Aristotle, whom you've probably heard of at this point, and he argued that matter is continuous. And what that means, let me change my color because red is kind of intimidating. He argued that matter is continuous, which means that you can keep breaking it up. There's no limit to how much you can break matter apart. So matter can be broken apart an infinite number of times. That was his argument. Democritus said, nah, bruh, I think you're wrong. Matter is discontinuous, which means that at some point, matter can no longer be subdivided, okay? So you reach a point where you can't break it apart anymore. You've reached the point where if you break this apart, you no longer have matter. And he called that point atomos. Sounds pretty similar to atom, right? I know. So these are the two arguments, continuous versus discontinuous. It turns out that Democritus was right, that matter at some point can't be subdivided. So some more time has passed, a lot more time has passed, and in 1803, John Dalton published the first atomic theory. John Dalton did a lot of work. This is just one of the things that he did. This is his atomic theory. There are 5 postulates or 5 points to his theory. You will need to know these and not just, repeat them verbatim. But if I give you a multiple choice question that says which one of these was, part of Dalton's atomic theory, or which one of these was not part of his theory, or after we get through chapter 4, you'll be able to say which one of these was proven to be incorrect. So those are the types of questions you'll need to answer, not just regurgitating information verbatim from the PowerPoint, okay? So that's just an aside. We'll talk about the types of questions, and you'll get to see those in class. So this is Dalton's atomic theory. An element is composed of tiny, indivisible, indestructible particles called atoms, okay? All atoms of an element are identical, and they have the same properties. So if you have a helium atom, doesn't matter where that helium atom is. It could be here, it could be in Thailand, it could be in Canada, it could be in Brazil. A helium atom is a helium atom everywhere. They're identical. They have the same properties. You can combine atoms of different elements to form compounds. We talked about what a compound is in chapter 3. Remember that a compound is a pure substance, right? And it's a pure substance that's made by mixing different elements. And those elements cannot be physically separated. So you're going to have to remember your vocabulary from chapter 3 to help you with chapter 4. The compounds that you can make with these different elements contain atoms in small whole number ratios. So you're not going to have half an atom of oxygen, okay? You can't do that. Everything has to be in whole numbers. And atoms can combine in more than one ratio to form different compounds. So one example would be H2O, that's water. H2O2 is hydrogen peroxide. Same two atoms, hydrogen and oxygen, but they have different ratios to one another. And those ratios govern what the different characteristics of the compounds are. So those are the 5 postulates of Dalton's atomic theory. And as we go through the models of the atom, you'll get to know which parts of his theory were correct and which parts were incorrect. Now we're going to talk about a person named J.J. Thomson, who, one, was credited with determining the charge to mass ratio of cathode rays, but he was also given credit for the discovery of the electron. Okay. Now you don't need to remember the dates, but you do need to know the names. Let me get fancy on y'all. That's a highlighter. Okay. So you'll need to know names. So know J.J. Thomson, or at least it's his last name, Thomson, and that he is credited with the discovery of the electron. You know, he had a proliferous lab, and he taught many people who then went on to further contribute to this field. So in my mind, that is even bigger than discovering the electron, but that you're actually able to impart knowledge and make scientists who can then go on and make other really important discoveries. So after he had this discovery of the electron and everything, he's toying around with these ideas in his mind about the atom, right? And he eventually proposes the plum pudding model in 1903. And what that says is that electrons were distributed evenly throughout a homogeneous sphere of positive charge. So over here on the right, what you'll see is this yellow cloud, right? That is the pudding. Which is the sea of positive charge. And the electrons, which are these little spheres with a negative in them, those are the plums, aka raisins. So you'll see plum pudding model. You'll also see raisins. Plums and raisins are the same thing in this context. I know we talk about plums as being the fruit, but just bear with me, okay? Those electrons are kind of like the little chunky stuff in the fruit. Now or in the pudding. I'm not any kind of a pudding person. Bread pudding, regular pudding. I don't do those things. But if you had pudding and there was something chunky in it, that would be the electrons. So that's his model of the atom. A few years after that, another person, Robert Millikan, whom you should know his last name at the very least, he determined the charge of an electron. So Thomson discovered the charge to mass ratio, and then someone else was able to build on that work to determine the charge of an electron. And then Thomson said, great, I can take that and calculate the mass of an electron. Okay. He also calculated the mass of a proton. We're going to kind of try to fit that into our timeline a little bit. But once that information about the mass of the electron, or excuse me, the charge of the electron was out there, then J.J. Thomson ran with it and did some calculations. Okay. Now, Ernest Rutherford, this is kind of in between the time of J.J. Thomson proposing his plum pudding model and Millikan doing the work to determine the charge of the electron. So the plum pudding model is like 1903. Millikan's work, that's 1911. Now we're looking at 1906. So we're kind of going forward, back, forward, back. We're going to do a little bit of a timeline in class to help put these things into context. So a former student of Thomson's, Ernest Rutherford, he went on to have his own lab, and he and his student performed a little experiment. You'll see it called the gold foil experiment. You might also see it called the alpha particle experiment. But most textbooks use some form of gold foil experiment. What they did was they took a very thin gold foil and they fired alpha particles at this foil. And what they're trying to figure out is this plum pudding model correct, or should we keep thinking? If the plum pudding model is correct, then there would be a lot of empty space in the atom. And there wouldn't be any kind of concentration of mass. So that would mean all the alpha particles, which are pretty heavy, would just pass right through. They'd go right through the foil, and they wouldn't be deflected at all. So that was their hypothesis. Assuming the plum pudding model is correct, these alpha particles should pass through this gold foil because it's mostly empty space. There's nothing there to stop these particles, nothing that's big enough to stop the particles or deflect the particles. What they actually saw was that some of the particles were deflected at a really large angle, or they were just, slightly deflected, right? So a lot of them just went straight through, but they saw some scattering, like here or here. What that means is that the alpha particles encountered something big. Something big enough to make them deflect. This is definitely not what they were expecting. So based on their results, they concluded that there must be some kind of a nucleus. There must be some kind of a concentrated mass that the alpha particles, which were scattered, encountered. Now, most of the particles, pass through the foil, so most of the atom is largely empty space. But at the center of the atom, there is this mass. And so it was proposed that this is the nucleus, which contains the protons, Nobody knew about neutrons yet. And then there's all this empty space. And of course, the electrons are in that empty space. But they're tiny. So Rutherford and his student, let's not forget the student, I was a grad student once, okay, they discovered the atomic nucleus and proposed a new model of the atom. That you've got this nucleus with protons and neutrons, you've got electrons hanging out in the space around the nucleus, but most of that space is kind of empty. They're also able to estimate sizes for these things, which they're pretty tiny. And based on how big the nucleus is that is able to deflect alpha particles, which are pretty large, neutrons were predicted, okay? And they were eventually discovered by James Chadwick. So he confirmed what Rutherford predicted must be true based on his observations. So that's the Rutherford model of the atom, that you have a nucleus and then a bunch of empty space plus nucleus. Let's try to spell it right. Y'all, I'm struggling with my writing right now. Must be mommy brain. Okay. There's the nucleus, and then there's electrons plus lots of empty space. Remember that this is the Rutherford model. So to summarize the subatomic particles that we're going to learn about in this class, which is based on the Rutherford model, we've got the electron. Here's its symbol, the E with the negative sign. It's located outside of the nucleus, and its relative charge is -1. I'm not going to have you worry about the mass too much, the relative mass. Just know that it's small, okay? Then there's the proton, which is positively charged, so its symbol is a P with a plus sign. It is inside the nucleus, and its relative charge is +1. Its size is comparable to that of the neutron. So that's what you should know. The electrons are very small. Protons and neutrons are about the same in size. The neutron, its symbol is N0. It's inside the nucleus along with the protons, and it has no charge. Okay, neutrons have no charge. Like I said, we're going to go through a little timeline and do kind of a history lesson at the beginning of our live lecture. So if you're watching this beforehand, kudos to you, because I know I'm getting it done late. I apologize. But you'll be able to kind of go back and put one together yourself, a timeline to help you place when these things happen and kind of see a bit of science in action. We always teach science as if it's set in stone and there's no discovery anymore, but that's very much not the case. Then folks like me would be out of a job. There'd be no reason to do research or no reason to be granted a degree because there's nothing to learn. But there's a lot to learn. It's just that some things we've learned a long time ago and they have not yet been challenged to be changed. So anyway, off of my soapbox. Now we'll move more into the concepts. So you'll need to know that little bit of history and how things led from one thing to another. Now we're going to talk about atomic notation and the periodic table and some other things. So each element on the periodic table has a certain number of protons. That number is called the atomic number, and it's abbreviated with a Z. So to rewrite that, atomic number equals Z, which is the number of protons in an element. The number of protons is what gives each element the different characteristics, okay? The total number of protons and neutrons in the nucleus is the mass number, which is abbreviated A. So the mass number is equal to A, which is equal to the number of protons plus the number of neutrons. When you see a symbol on the periodic table, you'll see one or two letters. The first letter will always be capitalized. And then up top, you'll see a number, and that is the mass number. And underneath that, you'll see the atomic number. So if we were to talk about carbon, the symbol for carbon is a C. Up top, you would see a 12. And at the bottom, you would see a 6. This 12 is protons plus neutrons. The 6 is just the number of protons. In a neutral atom, neutral, the atom has the same number of protons and electrons. So if you know how many protons there are, then you know how many electrons there are. And I'm stressing a neutral atom because we're going to talk about ions in the next chapter. And I don't want you to think, oh, well, you can't have different numbers. You can, but we're not talking about neutral atoms anymore. So let's talk through an example. We have silicon. Its symbol is Si. Notice how the first letter is capitalized and the second letter is not. The number at the bottom here, so this would be called a subscript, that is 14, and that's the atomic number, which is the number of protons. Above that, there's a superscript, which is the mass number, and that is the number of protons plus the number of electrons. And if you take the mass number, which is A, and subtract the atomic number, which is Z, then you have 29 minus 14 is equal to 15, and that tells you how many neutrons there are. So that's the information that you can get from the atomic symbol and atomic notation. All of the atoms of the same element, they don't have the same number of protons and neutrons. Some atoms have a different number of neutrons, and those are called isotopes. Okay, so same number of protons because they're the same element, but a different number of neutrons. That means that their atomic number is the same, but they have different mass numbers. So if I have carbon 12, carbon 13, carbon 14, these are all the same element. That's your Z, right? Your atomic number. But the mass number is different. So when you do the subtraction, you have 6 neutrons here, 7 neutrons, and 8 neutrons. That's just one example. This table has a number of examples of elements in their isotopes. You don't need to know this table. This is just for your reference. When you're referring to an isotope, you're usually going to refer to it as the element name followed by the mass number. So for carbon, you'd say carbon 12, or you'd represent it as a symbol like this. If we wanted to talk about carbon 13, you would write carbon-13, or the atomic notation. When we're talking about atomic mass, we're talking about the weighted average of all the known isotopes of an element. So we keep using carbon as an example because it's something that you've heard of carbon before. It's something that you can grasp, right? The weight that you see on the periodic table, so if you think about what it looks like, we're just going to take one little block, right? You'll see the atomic number up there, and then you'll see a number, usually it's a decimal, underneath. That number is the atomic mass, and each element has one. And what it does is it takes into account the weighted average mass of all the known isotopes. So we know about carbon 12 and carbon 13, however many isotopes there are, and the percentage of the element is which isotope. So the percent abundance of each isotope. What that means is, let's say that I have carbon 12, and carbon 13. Maybe I have 50% and 50%, which is unlikely. That means that half of the carbon in the world would be carbon 12, and the other half would be carbon 13. And when you calculate it, which I'll show you how to calculate the weighted average, when you calculate it, you'll see that the average mass is going to be somewhere in between the mass of carbon 12 and carbon 13. If, however, most of the carbon in the world is carbon 12, then you're going to see that the weighted average is going to be closer to the mass of carbon 12 versus carbon 13. So let's throw some numbers at this. All right. So I'm going to show you how I arrived at this equation here, okay? We've got gallium, and it's got 2 isotopes. Gallium-69, which has a mass of 68.926 AMUs. AMU stands for atomic mass units, okay? And this gallium-69 has a 60.11% abundance. I like to make a chart with this information because it helps me to organize things. So we've got our isotope, we've got our atomic mass, percent abundance. There's going to be a third column as well, but we'll leave that off for now. Our atomic mass, we were told, is 68.926 AMU, and the abundance is 60.11%. The second isotope for gallium is gallium-71. Its mass is 70.925 AMU, and its abundance is 39.89%. One thing that you should note is that we're talking about percent abundance, which means if you add these two up, you should get 100%. That's going to be important if you get a problem where you only get the percent abundance for all but one isotope. Then you'll have to figure out the percent abundance for that isotope and then continue on to do the math to figure out the weighted average for the atomic mass, okay? Now I said there's one more column. I like to rewrite the abundance as a decimal. So 60.11% as a decimal, you're going to move this decimal point to the right, or excuse me, to the left 2 times. That's what dividing by 100 does, okay? So as a decimal, 60.11% becomes 0.6011. Likewise, we're going to move that decimal 2 places to the left for the 39.89% and create 0.3989. Now we have to put together the calculation for the average atomic mass, which again is a weighted average. Takes into account not just what the mass is, but how much of the element is comprised of each isotope. This first part of the equation is the contribution from gallium-69. And all you're doing is taking your atomic mass and multiplying it by your abundance as a decimal. That's why I added this last column. You're going to add to that the contribution from the other isotope, in this case gallium-71. Multiply the atomic mass by its percent abundance written as a decimal. You add those two things together and you get 69.72 AMU. In terms of sig figs, we've got 4 sig figs from our abundance, and we've got 5 sig figs from the atomic mass. So the answer has to have 4 sig figs. The only way that this can become more complicated is if you have more isotopes or if one of the percentages is not included for the abundance, and you have to do the math to figure out what its percent abundance is before you can move on and calculate the average atomic mass. We will do practice for these in class, so don't you worry. But these are the basics. The biggest tip that I can give you, make a chart. Make a chart with the information from the problem, and then you'll know whether or not you have all the information to do the problem, and if you don't, what you need to calculate. So let's move on. I've been talking about the periodic table. We should probably show it a little bit. So we can use the periodic table to get information like the atomic number and the atomic mass. I may have written 12 instead of 6 for the atomic number for carbon. That's my bad. I'm not going to go back and check, but I feel in my spirit that I did, and I apologize. The atomic number is 6. The mass number is 12. Excuse my brain. We can talk about elements, neutrons, electrons, and all that stuff as particles. We can also talk about them as electrons, as waves of light. Okay? So before we can do that and put these concepts together, we need to first talk about the wave nature of light so that we can then go back and start talking more about the elements in the periodic table and how electrons can emit waves of light. Okay? So, light travels through space as a wave, and with that you have a wavelength, which is easier shown with an image. Okay, so the distance that the light travels in one cycle is the wavelength. So from peak to peak, that's a wavelength. That's a lambda. And that is a symbol for wavelength. You could also measure this from trough to trough. Same thing. The frequency, which we abbreviate with an F, is the number of wave cycles completed in each second. So how many times can you go up, down, up in 1 second? Light travels at a constant speed of about 3 times 10 to the 8th meters per second. When we compare wavelength and frequency, longer wavelengths of light have a lower frequency. They've got more distance to travel, so they can't travel as quickly, right? So you're not going to cover the same number of cycles in 1 second. So this top red line shows low energy, long wavelength light, and it's got low frequency. So long wavelength means low energy and low frequency. If you have a short wavelength, you're going to have high energy and high frequency. Now this is relative, of course, because there are different wavelengths of light, but whichever one is longer will have lower energy and a lower frequency. Since there are different wavelengths of light, we actually have a whole energy spectrum. It's called the radiant energy spectrum or the continuous spectrum, okay? Some of the things that you may be familiar with, everybody has a microwave, okay? Those microwaves, they're actual waves, okay? And it puts energy into your food to heat it up. We're also familiar with visible light because that's what we see. If you've ever been to the dentist, or if you, God forbid, have broken a bone or something like that, you've experienced x-rays, okay? Everybody watches TV, you've experienced cable TV or something like that. Maybe you listen to the radio, 102 jams or something on your way to and from the job, right? All of those things are waves of light. Starting with radio waves, these are low energy, long wavelengths, which is already written up here. But you know I like to write as I talk. I can't help it. As you move from right to left on this figure, you are going to increase your energy and increase your frequency and decrease your wavelength. So cosmic rays, we're talking about like, out in space. High energy, very short wavelengths. You will need to know the visible spectrum in terms of the colors and where they fall. So if you ever had to learn the rainbow, it's usually taught Roy G. Biv. So you've got red, orange, yellow. That's Roy. G is green. Then we have blue, indigo, which is a deeper blue, and violet, purple. Okay. So you will need to know the order of visible light in order to compare. So if I say which one has a higher frequency, orange light or indigo light, you should tell me indigo. So you'll need to know the relative order of these. You won't need to know the wavelength specifically, but you'll need to know the relative order of these in order to compare them on an exam. So this again is just the visible light spectrum. We already covered the order of the rainbow, okay? So we talked about light as a continuous spectrum. Now we need to take that concept of light and how it can be emitted as a wave and apply it to our model of the atom. Electrons can get excited, and then they can also fall back down to kind of a ground state. Kind of like if you give kids, or anybody really, a bunch of sugar, you might see them get super excited. Maybe they're a little bit wound up, see some crazy energy release, and then they crash. Or they at least just go back to normal, right? That's going from the excited state back down to ground state. When that happens, the energy that's released for an electron to do that, it's packaged in small discrete bundles. So to talk about energy continuous versus these quantized small bundles, if you think about a ball rolling down a ramp, it's just going to roll all the way down, right? But if you have a ball going downstairs, or a slinky, which I don't know if anybody knows what a slinky is anymore. YouTube it. Those old commercials are there from the 80s. If you're going up or down the stairs, you have to lift your foot up a certain amount or put your foot down a certain amount to go from one step to the next. That's quantized. You can't go down half a step. Your foot would just be floating there, right? Then you ain't going nowhere. With this tennis ball, it has to lose a certain amount of potential energy for each step that it falls down. It can't lose more than that because then it'll miss the step. If it loses less than that, it's not going to fall. It's the same thing with electrons. Electrons can gain or lose energy in small, discrete bundles. That leads us to the Bohr model of the atom. So he said, okay, we've got the Rutherford model, that's great, but we need to add some more to it. So the electrons that orbit the nucleus are in fixed energy levels, okay? They're only found in these energy levels, these specific energy levels, and nowhere else. That they're quantized. What that means is there's different levels. So if you have an electron or two electrons and n equals 1, that's energy level 1, and you want to get it to energy level 2, you have to feed it a certain amount of energy for it to jump up to n equals 2. There is no n equals 1.5. There's no n equals 2.7, okay? We're talking about whole numbers here. So that doesn't exist. Electrons are only found in these specific energy levels, and in order to move up or down, they need specific amounts of energy, and we call that quantized energy or quantized energy levels. Some of the support for that comes from emission line spectra. If you have a gas of any element in a lamp, in this case we have hydrogen gas here for this example, and you put voltage through it, and then you send that light through a prism, which is going to separate out the different colors, you will only see certain colors come out. Remember that these colors that you see are different wavelengths of light. And you don't see a smear of colors. You see distinct bands. That means that you're only getting certain amounts of energy being released when these excited electrons return to their ground state. So that supports the idea that there are energy levels and there's nothing in between them. There's no, if you're in n equals 1, you need a certain amount to get to n equals 2. And each element has its own atomic fingerprint. So you can do this with helium, lithium, sodium, all the different elements, and you will see a different emission line spectrum for each element. So it's kind of like a fingerprint. You can tell what you have based on what you see here. And they're always discrete bands. Not a smear of colors, not a tie-dye shirt. We're talking about distinct lines in each spectra. So Bohr had it mostly right, okay? That you have these quantized energy levels. You've got your nucleus in the center. And then each of these numbers represents an energy level. And the higher the energy level, the further away that electron is from the nucleus. Now, it turns out that the energy levels aren't fixed, that you can, put energy into the system and those electrons can get excited, they can release energy and come back down, okay? So they're not fixed, but they are quantized. Within each energy level, there are energy sublevels. So if you think about going to a mall, like a legit mall, where there's, 2 or 3 levels, you can be on level 1, level 2, level 3, but within that, it's not just, there's different stores, right? It's broken up a little bit differently. Maybe the food court is here, maybe there is an arcade. I'm old, they don't have arcades anymore, but you know what I'm talking about. Maybe the next level, they have hair salons and, particular department stores and stuff like that. The third floor might have all of the games and video game shops and that kind of stuff. So it's different levels representing the different energy. And then within that, there's some kind of division, okay, of each energy sublevel. The sublevels are given designations S, P, D, and F. You don't need to understand the, why they're designated this, all right? That's there for your own information. But you do need to know S, P, D, and F. Those are the energy sublevels. The number of sublevels in each level is the same as the number of the main energy level. So if you're in N equals 1 and there's an S here, then you're in the 1S. If you're in energy level 2, then you're in the 2S. So that's what that means. This 2, this 1, that's the main energy level, okay? The first energy level just has the 1S. Second energy level has S and the P. Third has S, P, and D. And I will tell you more about this order. But what I want you to notice is that the further away the sublevel and the energy level is, or the higher the number, the further away it is. So here we've got low energy, higher energy. So remember that. The further away you are from the nucleus, the higher the energy level you have. So that electron is going to have more energy. This tells you the maximum number of electrons that each energy level or sublevel can hold. So S, no matter which energy level it is, can only hold 2 electrons. The P sublevel can only hold 6, D can hold 10, and F can hold 14. And we're talking about a maximum. So you can have a partially filled S or partially filled D, okay? All of this information is leading up to being able to write electron configurations. So it may seem a little bit piecemeal, but we've got to build all of this information about the model of the atom, what the electrons can do, where they can be, and then we can write something that details where the electrons are in a ground state atom. This table here tells you the distribution of electrons by energy level. It only goes up to 4, but there's actually a 5, a 6, and a 7, okay? And don't worry, I will show you all of that. For each energy level, you can have certain sublevels. So in the energy level 1, there's only the S. In energy level 2, you have 2S and 2P. Energy level 3, you have 3S, 3P, and 3D. Each of those sublevels can only hold a certain number of electrons, but each main energy level can hold more and more electrons. So energy level 1, you can only hold 2 electrons, and they're in the 1s. Energy level 2, well, you've got the 2s, which can hold 2 electrons, plus the 2p, which can hold a total of 6 electrons. That gives you a total of 8 electrons that you can add before you have to move up to the next energy level. In energy level 3, you can have the 2 in the S, plus the 2 in the P, plus an additional 10 in the D, and that gives you 18 electrons in level 3. Same thing for the 4. You're going to have the 2s, or the 4s with 2 electrons. The 4p, you have 6 electrons. 4d up to 10. And then the 4f is up to 14. And that equals 32. So if you had an element that had everything filled up to the 4f, then what you would have is an element with 2 plus 8 plus 18 plus 32 electrons. And if you do that math, you would get 60. So that's what this means. The total number of electrons that you can have if you were to fill all of these energy levels completely. Now there's an order to how these energy levels are filled, which we're going to get to in just a second. But I want you to grasp the idea that what we're talking about is maximum. So the 1s can hold up to 2 electrons, but it can also just hold 1. But if you have 3 electrons, then you need to spill over into the next energy level. And that's how you're filling the energy levels, and you're going across the periodic table as you increase in your atomic number and increase the number of electrons you have. So this kind of describes what I was describing on the last slide with the table, but it's just in words that you can read. So the electrons are arranged around the nucleus. First electrons that are filled are closest to the nucleus, and then you just keep going further and further out the more electrons you have. This is a partial list of the sublevels, but I'm going to give you the whole thing, okay? Because you're going to need to know this in order to fill all of the energy levels when we're writing electron configurations. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, okay? Then 4p, 5s, then 4d. Then you're going to fill the 5p, the 6s, then you're going to start to fill the 4f, followed by the 5d, 6p, 7s, 5f, 6d, and then 7p. So this is the full list of sublevels and how they increase in size. So as you're filling your electron energy levels, you're always going to fill the 1p first, then the 1s first, then the 2s, then the 2p, and you're going to fill until all of your electrons have been placed. So what does that mean? We're going to go back to our handy carbon example. And this time I'm going to write it correctly. Let's say that we want to write a diagram or a configuration for carbon. This 6 is the number of protons. And in a neutral atom, that's also equal to the number of electrons. So that means carbon has 6 electrons that we need to place. So I'll write out the order just for a little bit. I know that I'm not going to need more than the 3p, okay? Now, you'll also need to know how many electrons each sublevel can hold, which we went over just a second ago. Remember that the S can hold 2 electrons, the P can hold up to 6, the D can hold up to 10, and the F can hold up to 14. I have 6 electrons to place. Each of these you can think of as, all right, I've got one place here, got one place here. There are actually 3 slots for electrons in the P. There are 3 P suborbitals, okay? We're going to talk about that in just a little bit. But if I were just filling in the numbers, I'd say, okay, I need to fill in my 1s. I need to fill in my 2s. So I've got 2 plus 2, cool. Now I need to fill in my 2p. And that equals 6 electrons. If I were writing this as a configuration, my 1s is full. So this number at the top tells me the number of electrons in a given sublevel. I have to fill my 1s before I can move on to anything else. So I filled my 1s. We started with 6 electrons. Now I've got 4 electrons left to place. I fill up my 2s with another 2 electrons. So now I've got 2 electrons to place. I put those other 2 into the 2p. And now I've got 0 electrons left. So the configuration is 1s2, 2s2, 2p2. This is something that takes practice. There's a bunch of different ways that you can kind of conceptualize how to do it. And I found a video on YouTube that has a really good visualization of this. So I put that link into the Chapter 4 folder as well. So if electron configurations are making your brain explode, watch that video. There's no use in remaking the wheel. Someone else made a really good video about it that helps you visualize it. And it's only like 7.5 minutes long. But I promise you, it will help make this concept make sense. And we'll do more practice. So we already went over writing electron configurations kind of by doing a problem, but I also wanted to put it in words because some people they understand things better when they can read it versus seeing it. So you have an electron configuration that's shorthand for writing where the electrons are. You use superscripts and the sublevels, right? And the energy sublevels are arranged in that order, that long order that I told you, in increasing energy. This is the periodic table. This isn't the exact one that you're going to get for your exams and everything, but I wanted to use a prettified, colorful one because that's just what I like, okay? We can break up the periodic table according to which orbital is being filled. So these first two columns, they're always going to be filling the s orbital. So it's called the s block. The next section is called the d block, and that's because it's filling the d orbital. After that, you have the p block, because you're filling the p. So wherever the element is, S block, D block, P block, and at the bottom here is F block, because you're filling the F orbital. Wherever the element is, that's going to tell you the last orbital that should be in your electron configuration. So if I'm writing a configuration for calcium, it's in the S block. So the final thing that I write for my configuration, the last sublevel, should be S something. Each row of the periodic table is the main energy level. So that's our N. So the calcium that I was talking about before, it should be filling its 4s2. See, that's the main. We're in S block, and it's 1, 2. So that should be the last thing that you write in your electron configuration. If we were going to write the full-on configuration for calcium, we could literally walk it across. You start up here with hydrogen. Hydrogen is in energy level 1. And so is helium, okay? So if we fill both of these, it's 1s2. And I should not have put, helium is also kind of a part of the S block. There's only S in the first energy level. But helium is a noble gas, so it usually gets put on the other side of the table. It's confusing, I know. But if we're filling this first N equals 1 level, then that means that we have 1s2, okay? The second energy level, we're filling 2s2, because we haven't gotten to calcium yet. Then we're filling all of the P, and the P can hold a total of 6. We haven't gotten to calcium yet, so we have to keep going across the table. So now we're at row 3. We're in the S block, and we filled it, 3s2. Then we go further across, and we fill the 3p. That's 3p6. Now we're finally in the 4, right? And our calcium has filled the S block. So this is the configuration for calcium. Let's say that we wanted to do chromium instead. Chromium has everything that calcium has. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, but it's in the D block, right? And the D is always going to be one less than the main energy level that you were just at. So we were just at the 4s, so now that D is going to be 3D. How many have filled in the D? 1, 2, 3, 4. We're at chromium. So we moved 4 elements over from calcium to chromium, and all we had to do was add 3d4 to show the difference between the electron configuration for calcium and the configuration for chromium. So if that still doesn't help you understand how to write electron configurations, don't worry. We're going to do it in class, and there's a video that I've already posted that gives a great visual of what you're doing when you're filling these orbitals. Practice makes perfect. Again, this is another example in words because some people work better with words. So you can read through this example and understand how to write an electron configuration, in this case for bromine. So I'm not going to walk through this one, but this is for all of you that are you need the words on the screen to help you process. So here I have 2 examples which we're going to work on in class, but I wanted to give them to you so that you can practice on your own. I'm not going to give you the answers here, but practice writing the electron configuration for copper, which has 29 electrons, and neodymium, which has 60 electrons. Again, we're going to go over it in class, but I just want to give you the opportunity to do it and encourage you to come to class to watch the live lecture and get that kind of feedback, all right? Now we're going to bring together the different models of the atom and kind of land on where we are today, which is the quantum mechanical model. We went through the Rutherford model, where we said, okay, there's some kind of a nucleus that has concentration of mass and a lot of space, and in that space there's electrons. And then Bohr added on to say that those electrons are in fixed energy levels. The quantum mechanical model says, well, there are energy levels and they're quantized, but they're not necessarily fixed. You can move from one energy level to another. You're just increasing energy or you're decreasing energy. And these electrons that are in these main energy levels, we can break those down into orbitals, S, P, D, and F, which we were talking about when we were doing the electron configurations. An orbital is the region of space where you've got a high probability of finding an electron. The higher the energy of the orbital, the larger it is. So if you have a 4s and a 2s, the 4s is going to have a higher energy because there's the 4 for the main energy level, okay? So if we were going to draw kind of an idea, the 2s would look like this, and the 4s might look like this. The way that I think about it is when you were 5 years old, you couldn't go very far, right? Your parents had to be right there. You weren't allowed to walk down the street. When you're 15, you could walk down the street to a friend's house, or if you're stopping by the store, your parents don't want to get out the car, go in there and get me some milk and eggs. Come right back, right? So you can go a lot further. The distance between your parents or your house and where you can be increases as you get older. The same thing when it comes to the energy levels with electrons. The bigger the energy level, or the bigger the energy of an orbital, the bigger its size. So the further away electrons can be from the nucleus. Because remember, the nucleus is a little dot in the middle, and the electrons are all around that. And the higher the energy, the further away electrons can be. We're going to talk a little bit about the shape of the different orbitals, and then we'll be almost done. So all s orbitals are sphericals. Sphericals, goodness gracious. It's too many s's, y'all. All s orbitals are spherical. So it doesn't matter how big the energy level is, it's always going to be the same shape. But just like before, the 1s is smaller than the 3s, right? Higher energy, larger orbital. The p orbitals are shaped like dumbbells, okay? And there's 3 different sublevels. Remember that they hold a total of 6 electrons. That's because there's, for example, in energy level 2, you can have X, Y, and Z for the P, okay? And each of those can hold 2 electrons, which are represented by those little arrows. And the X, Y, and Z just tells you the orientation. So you can have an electron that's in this kind of, you can think of it as a figure 8 or a dumbbell, whichever one. So there's the X, or you can have it on the Y axis, or you can have the electron on the Z axis. Okay. All 3 of them together looks like this. So if you have all 6 electrons hanging out in the 2p, then you're going to have them kind of doing these figure 8s, all right? So that's the shape of the p orbital. For the d, there are 5 different d sublevels, okay? The shapes of them are a little bit funky, so some of them, most of them, have this kind of clover leaf shape. But one of them has to be the special child. And it's kind of like a dumbbell that we saw with the 2p, plus this kind of weird donut shape. So that one's a little bit funky. But all you need to remember is that there are 5 different d sublevels in the d orbital, okay? So that's 1, 2, 3, 4, 5 d sublevels. So let's say that we're talking about the 3D, 3D YZ, 3D XZ, and so on and so forth. And each of these can hold 2 electrons for a total of 10 electrons in the d orbital. We're not going to talk about the F shape because that's something else, okay? But I do want to remind you about dates for things. So you have Chapter 4 check-in due on Sunday the 20th. You also have Mastering Chemistry homework and your quiz due on the same day. So don't wait, get started. This shouldn't be too bad. The hardest part is the electron configuration. Everything else you should be able to get through. You may have to practice with the weighted averages, but those are really the 2 most difficult parts of Chapter 4. Okay, everything else is really concepts. Your Exam 2, which I know Exam 1 hasn't fully been taken yet, thanks to respondents having issues, but Exam 2 is coming up on September 23rd. And that's going to cover Chapters 3 and 4. Remember, Chapter 3, we did the states of matter. and we did like physical changes and physical properties and all those kinds of things, and began to introduce the periodic table. And then today, whenever you watch this, we're talking really about the atom. We started talking about the periodic table. We'll do more discussion of the periodic table in chapter 5, which is coming up. So, recap. Homework. September 20th. There's check-in and there's mastering chemistry. We'll do some practice problems. Make sure you're good to go. And then you'll be off to the races, doing your homework, and staying caught up, please. Please, please, please. 40% of your grade is this. Don't let it slide. 40%, that's almost half of your grade based on homework that you can do spread out throughout the course of about a week. So please, 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 please do your homework. If you don't do your homework, I can't help you. I can't help you. So get started. And if you have questions, you can always come to office hours. All right. That's all I have for you. I'll see you in class.